There's a particular quality to silence that arrives when you step outside on a clear winter night and look up. The air is cold. Your breath clouds in front of you. And above, scattered across the darkness, are points of light that have been traveling for years, decades, centuries, just to reach your eyes in this moment. We often think we know the night sky. We recognize constellations, perhaps. We know the moon. We've heard of distant galaxies. But there's something remarkable about how little we actually think about the individual stars themselves, not as abstract dots, but as singular, immense, powerful entities. Each one a furnace, each one a story unfolding across time so vast, it makes human history feel like a single breath. And among them, there is one star you have almost certainly seen, many times, without ever pausing to wonder what it truly is. It doesn't demand your attention. It doesn't flash or pulse or announce itself. It simply hangs there, a faint reddish glow in the winter sky, older than most of the stars around it, larger than almost anything you could imagine, quietly approaching the end of a life that has already lasted millions of years. You've looked at it without knowing you are looking at one of the most extraordinary objects in our galaxy. Its name is Betelgeuse. Before we try to understand what Betelgeuse is, let's return to that feeling. The one you get when you're standing beneath the stars, alone, aware that something immense is happening just beyond your comprehension. There's a certain kind of smallness that comes with stargazing. Not a diminishing smallness, but something else. A realization that you are witnessing something far older and far larger than yourself, and that this witnessing is, in its own quiet way, profound. The stars have been there long before you were born. They'll be there long after you're gone. And yet, in this moment, they exist for you. The light they emitted years ago has crossed unimaginable distances just to reach your retina, to trigger neurons, to create the sensation of seeing. In a sense, you and the star are connected across space and time, however briefly, however tenuously. And there's one star in particular that embodies this connection more than almost any other. There's a star in the constellation Orion. If you know Orion, you know the hunter's shape, the three bright stars that form his belt, the faint stars that trace his sword, the distinctive hourglass silhouette that has guided travelers and dreamers for thousands of years. And if you look carefully at Orion's shoulder, the upper left star from your perspective, you'll see it, Betelgeuse. Even in casual observation, there's something different about it. While most stars appear white or pale blue, Betelgeuse glows with a warm, amber-red hue. It doesn't shine with the crisp brightness of Sirius or the steady constancy of Polaris. Instead, it flickers. It dims and brightens unpredictably, as if breathing. The ancient Arabic astronomers called it Yad al-Jawza, the hand of the central one. The name eventually became corrupted into Betelgeuse, though some prefer the pronunciation Betelgeuse, which has led to its own cultural associations. But names aside, what matters is what it represents. A marker in the sky that humans have observed for as long as we've had the capacity to look up and wonder. For most of human history, this star has been a marker of seasons, a reference point for navigation, a character in mythology. The ancient Egyptians saw it, the Babylonians recorded its position. Medieval astronomers charted its movements. Indigenous cultures around the world wove it into their stories of creation and time. The Lakota people saw it as one of the hands of a great chief. The Yolngu people of Australia incorporated it into their songlines. Japanese astronomers in the Edo period meticulously recorded its color and brightness. And yet, until very recently, almost no one truly understood what they were looking at. What we now know is this. Betelgeuse is not simply a star. It is a red supergiant, one of the largest, most luminous, and most volatile stars known to exist in our region of the Milky Way. If you could somehow place Betelgeuse at the center of our solar system, where the Sun currently resides, its surface would extend past the orbit of Mars, possibly past Jupiter. The Earth, Venus, Mercury, all of the inner planets would be consumed, vaporized, absorbed into the outer layers of this single, incomprehensibly massive sphere of plasma. And it is dying. Let's slow down for a moment. When we say a star is dying, we're not using metaphor. We mean it in the most literal, physical sense. Stars are not eternal. They are born, they live, and they die, but on timescales so far removed from human experience that we rarely internalize this fact. Our Sun, for instance, has been burning steadily for about 4.5 billion years. It will continue to burn, mostly unchanged, for another 5 billion. To us, it feels permanent, reliable, a constant. But stars like Betelgeuse live differently. Betelgeuse was born roughly 8 to 10 million years ago, a relatively short time in cosmic terms, yet still longer than the entire span of human evolution. When Betelgeuse first ignited, our ancestors were still millions of years away from walking upright. The lineage that would eventually lead to humans was still swinging through trees, small-brained, unremarkable. The star formed from a collapsing cloud of gas and dust, igniting in a burst of nuclear fusion as hydrogen atoms fused into helium, releasing tremendous energy in the process. This is how all stars are born. Gravity pulls matter together until the pressure and temperature at the core become so intense that atomic nuclei overcome their natural repulsion and merge, releasing energy in the process. For stars like our Sun, this is a process that can continue for billions of years. The Sun is a steady, reliable furnace, burning its fuel at a measured pace, maintaining equilibrium between the outward pressure of fusion and the inward pull of gravity. But unlike our Sun, which will spend billions of years in this stable phase, massive stars like Betelgeuse burn through their fuel at an astonishing rate. They are profligate, wasteful, radiant beyond measure. They shine with the brightness of tens of thousands, even hundreds of thousands of suns. And because they burn so fiercely, they exhaust themselves far more quickly. Think of it this way. If the Sun's fuel supply is like a carefully managed trust fund, meant to last a lifetime, Betelgeuse's fuel supply is like a lottery winner who burns through their winnings in a few short years of extravagant living. The star shines brilliantly, it lives magnificently, but it cannot sustain itself. Betelgeuse has already passed through the phase where our Sun currently resides. It has consumed all the hydrogen in its core. Then it consumed helium, fusing it into carbon and oxygen. Now it is fusing heavier and heavier elements, oxygen into neon, neon into magnesium, magnesium into silicon, climbing the periodic table step by step, in a desperate attempt to sustain itself against the crushing force of its own gravity. Each stage happens faster than the last. Hydrogen fusion lasts millions of years. Helium fusion lasts hundreds of thousands. Carbon fusion lasts centuries. Silicon fusion lasts days. And then, inevitably, the core fills with iron, and everything stops. It's worth pausing here to consider what we mean by collapse. For millions of years, a star like Betelgeuse exists in a kind of equilibrium. The outward pressure generated by nuclear fusion in its core pushes against the inward pull of gravity. As long as fusion continues, the star remains stable. Swollen, yes, and chaotic, but structurally intact. But once the core is filled with iron, fusion stops. Iron is the end of the line. It's the most stable element in terms of nuclear binding energy, which means fusing iron requires more energy than it releases. There is no more fuel, no more outward pressure. The star has reached the limit of what chemistry can do. And in an instant, literally in less than a second, the core collapses under its own weight. Imagine an object roughly the size of Earth, made of iron, collapsing to the size of a city. Then imagine it collapsing further to the size of a mountain, then to the size of a building, all in less than a heartbeat. The density becomes so extreme that electrons are forced into protons, creating neutrons. The core becomes a neutron star, an object so dense that a single teaspoon of its material would weigh as much as a mountain on Earth. What happens next is almost too violent to comprehend. The collapse is so sudden, so complete, that the core rebounds. The outer layers of the star, still falling inward at significant fractions of the speed of light, smash into this rebounding core and are blasted outward in an explosion of unimaginable scale. For a few weeks, the dying star shines brighter than an entire galaxy containing hundreds of billions of stars. It releases more energy in those weeks than our sun will emit over its entire 10 billion-year lifetime. This is a supernova, and Betelgeuse is on its way to becoming one. Not tomorrow, not next year, but soon, in astronomical terms. It could happen in our lifetimes. It could happen in 10,000 years. The uncertainty itself is part of what makes it fascinating. We are watching a star in the final, unstable stages of its existence, knowing that at some point, unpredictably, suddenly, it will end. Now, before we let this become a story of endings, let's pause and appreciate what Betelgeuse actually is in this moment, right now, as it exists in the night sky. Imagine standing on a hypothetical planet orbiting Betelgeuse at a safe distance, far, enough that the heat doesn't vaporize you, but close enough to witness the star's true nature. What would you see? First, the star itself. It would dominate the sky, not as a point of light, but as an immense, roiling sphere, filling a significant portion of your view. Its surface wouldn't be smooth or uniform. Instead, you'd see vast convection cells, each one larger than the sun, churning and bubbling as superheated gas rises and cooler gas sinks. The temperature at the surface is relatively cool for a star, around 3,500 Kelvin or about 5,800 degrees Fahrenheit. That's why it appears red rather than white or blue. But cool is relative. This is still hot enough to vaporize any known material instantly. Enormous plumes of material would erupt from the surface, casting off shells of gas and dust into space. These ejections are so massive that they can temporarily obscure large portions of the star, causing it to dim as seen from Earth, which is exactly what happened in 2019 and 2020. An event we'll return to shortly. The color would shift, deep red, fading to orange, flickering with brighter spots where hotter regions break through the cooler outer layers. The light would be so intense that even at a distance where the heat was survivable, the sky would never truly be dark. Shadows would be soft and diffuse. The horizon would glow with a perpetual crimson twilight. And if you could somehow measure the star's heartbeat, the pulsations that cause it to dim and brighten, you'd realize it was unstable in a way our sun never has been. Betelgeuse expands and contracts irregularly, driven by complex, chaotic processes deep within its interior. These pulsations aren't gentle. The star's radius can change by hundreds of millions of miles over the course of months or years. Imagine the sun suddenly swelling to engulf Earth's orbit, then shrinking back, then swelling again, all while continuing to shine with undiminished fury. That's what's happening at Betelgeuse constantly, unpredictably. Sometimes these pulsations are somewhat regular, following patterns that astronomers can track and predict. Other times they're not. The star seems to have multiple pulsation modes overlapping, creating a complex rhythm that we're still working to understand. In late 2019 and early 2020, Betelgeuse dimmed dramatically, far more than astronomers expected. For a few months, it became noticeably fainter in the night sky, dropping to roughly 40% of its normal brightness. This was visible even to casual observers who knew where to look. For a brief, exciting moment, speculation ran wild. Was Betelgeuse about to explode? Were we witnessing the final stages before a supernova? Astronomers scrambled to observe, to measure, to understand what was happening. Telescopes around the world and in space turned toward Orion. Data poured in, and gradually, a picture emerged. What they eventually determined was both simpler and stranger than a supernova. Betelgeuse had ejected a massive cloud of gas and dust from its surface, far more than usual. This cloud then cooled and condensed, forming a dark, opaque mass that temporarily blocked much of the star's light from reaching us. It was, in essence, a titanic stellar sneeze, a reminder that even without exploding, stars of this scale are capable of reshaping their surroundings in ways that beggar imagination. The dimming passed, the dust dispersed. Betelgeuse brightened again, and in fact became brighter than it had been before the event, likely due to the natural variations in its pulsation cycle. But the event reminded us of something important. We are watching a star in real time, in the final, unpredictable stages of its life. Every observation is precious. Every measurement adds to our understanding of a process we've never witnessed up close. Because here's the thing, we've never actually watched a red supergiant explode. We've seen the aftermath. We've studied distant supernovae in other galaxies. We've built detailed computer models, but we've never been able to observe a star like Betelgeuse in detail before it exploded, tracking its behavior, its changes, its final moments. When Betelgeuse finally goes supernova, it will be the most closely observed stellar death in human history. And everything we learn from it will reshape our understanding of how massive stars die, how elements are created, and how the universe recycles matter. That's what makes the 2019 to 2020 dimming event so valuable. It gave us a preview, a glimpse of the kind of instability that characterizes the end stages of a red supergiant's life. And it reminded us, this star is not stable. It is chaotic, violent, and unpredictable. And it is dying. Let's zoom out for a moment. Betelgeuse is approximately 650 light-years away from Earth. Some measurements suggest it might be slightly closer, perhaps 550 light-years. Others suggest it might be farther, perhaps 700 light-years. The uncertainty comes from the difficulty of measuring distances to stars accurately, even with modern techniques. But regardless of the exact number, the distance is almost impossible to visualize in any meaningful way. So let's try a few comparisons. A light-year is the distance light travels in 1 year, moving at 186,000 miles per second. That works out to about 5.88 trillion miles per year. 650 light-years, then, is roughly 3,800 trillion miles. If you were traveling at the speed of the fastest spacecraft humanity has ever built, the Parker Solar Probe, which reaches speeds of about 430,000 miles per hour when it's at its closest approach to the Sun, it would still take you roughly 1,000 years just to reach the nearest star beyond our Sun, Proxima Centauri. To reach Betelgeuse at that speed would take hundreds of thousands of years. Generations would be born and die aboard the spacecraft. Civilizations would rise and fall back on Earth. Languages would evolve beyond recognition. And all the while, the spacecraft would be traveling through the void, crossing the immense, empty spaces between stars, heading toward a point of light that grows infinitesimally brighter with each passing century. Light, moving at its theoretical maximum speed, takes 650 years to make the journey. This means that when you look at Betelgeuse tonight, you are not seeing it as it exists now. You are seeing it as it was in the year 1375. Think about that year for a moment. In 1375, the Renaissance was just beginning to stir in Italy. The printing press had not yet been invented. The Ming dynasty had recently come to power in China. The Aztec Empire was still establishing itself in what is now Mexico. Most of the world's population had never heard of the Americas. That's the light you're seeing. Light that left Betelgeuse's surface during the late Middle Ages, carrying information about the star's temperature, brightness, composition, and motion. And this raises a humbling, quietly astonishing possibility. Betelgeuse may have already exploded. The supernova could have happened decades ago, centuries ago, and we wouldn't know yet. The light from that explosion could be racing toward us at this very moment, crossing the vast, silent distances between stars, carrying news of an event that has already reshaped a small corner of the galaxy. It could arrive tomorrow. It could arrive while you're reading this. Or it could not arrive for another 100,000 years. We simply don't know. What we do know is that, on cosmic timescales, it will happen soon. Betelgeuse is already in the final stages of its life. All the heavy elements have been created. The iron core is growing. The end is approaching, not in human time, but in stellar time. And when it happens, whenever that may be, we will see it. Assuming, of course, that we're still here. Assuming that human civilization survives long enough to witness it. Assuming that there are still people looking up at the night sky, wondering about the stars, caring enough to notice when one of them suddenly, dramatically, changes. That's not guaranteed, but it's possible. And the possibility itself is worth considering. There's something strange about contemplating the death of a star from such a distance. On the one hand, it's abstract. We know, intellectually, that supernovae happen all the time throughout the universe. Every second, somewhere in the cosmos, a massive star reaches the end of its life and explodes. These events are common, natural, inevitable. Astronomers estimate that in a galaxy the size of the Milky Way, a supernova occurs roughly once every 50 years on average. Some years there might be none. Other years there might be several. But over long timescales, the rate is fairly consistent. Most of these supernovae happen so far away that we never see them. They occur in distant spiral arms behind clouds of dust, in regions of the galaxy that are permanently obscured from our view. Or they happen in other galaxies entirely, millions or billions of light years away, visible only as faint smudges in the most powerful telescopes. And yet, there's something deeply personal about Betelgeuse. This is a star we can see. A star that has been part of the human experience for as long as humans have looked up. It has appeared in our stories, our myths, our art. It has guided sailors across oceans. It has marked the turning of seasons for farmers and herders. It has been painted, photographed, and written about. It is, in a small but real way, part of our shared history. The ancient Greeks associated Orion with a great hunter, and Betelgeuse was his shoulder or arm. Arab astronomers saw it as the hand of the giant. Chinese astronomers included it in their constellation of the 4 stars of the pivot, marking the center of the heavens. Indigenous Australian cultures saw it as part of their intricate star maps, which encoded seasonal information, navigation routes, and sacred stories. In Polynesian navigation, the rising and setting of Orion, including Betelgeuse, helped sailors navigate thousands of miles across open ocean, reaching islands separated by vast expanses of water with remarkable precision. This star has been watched, studied, and wondered about by countless humans across countless cultures. It is woven into our collective consciousness in ways we rarely stop to acknowledge. And one day, maybe in our lifetimes, maybe not, it will vanish from the night sky in a blaze of light so bright it could briefly rival the full moon. For a few weeks, we would have two bright lights in the night sky: the moon and Betelgeuse, a dying star shining with the fury of its own collapse. You'd be able to see it during the day, a bright point of light visible even when the sun is up. It would cast shadows at night, turning darkness into a kind of dim, eerie twilight. And then, gradually, it would fade. The peak brightness would last only a few days. Within a week, it would begin to dim. Within a few weeks, it would be fainter than the full moon. Within a few months, it would require a telescope to see. And within a few years, it would fade to the point where only the most sensitive instruments could detect it. What would remain, invisible to our eyes but real nonetheless, would be a remnant. Either a neutron star, an object so dense that a teaspoon of its material would weigh as much as a mountain, or possibly a black hole. A point in space where gravity is so strong that not even light can escape. The choice between neutron star and black hole depends on the exact mass of Betelgeuse's core at the moment of collapse. Current estimates suggest Betelgeuse is right on the borderline. It could go either way. If the core is slightly less massive, it will become a neutron star spinning rapidly, possibly emitting beams of radiation as a pulsar. If the core is slightly more massive, it will collapse past even the neutron star stage, becoming a black hole. A region of space-time so warped that nothing, not even light, can escape once it crosses the event horizon. Either way, the result will be extraordinary. A stellar corpse compressed to a size smaller than a city, containing more mass than our entire sun, and the gas and dust expelled in the explosion would spread outward at thousands of miles per second, mingling with the interstellar medium, eventually seeding new clouds of gas that would, millions of years from now, collapse to form new stars. In this way, Betelgeuse's death would not be an ending. It would be a transformation, a return of its material to the galaxy, a continuation of the cycle that has been unfolding since the first stars ignited, billions of years ago. It's worth asking, why does any of this matter? Why should we care about a star so far away that its light takes centuries to reach us? Why spend time trying to understand the physics of stellar evolution, the mechanics of supernova, the eventual fate of objects we will never touch, never visit, never influence in any way? There are practical answers, of course. Studying stars like Betelgeuse helps us understand the life cycle of matter in the universe. It reveals how heavy elements, carbon, oxygen, iron, gold, are forged in stellar cores and scattered into space, eventually becoming part of planets, oceans, and living organisms. Every atom in your body, except for hydrogen, was created inside a star. The hydrogen itself dates back to the Big Bang, formed in the first few minutes after the universe began. But everything else, the carbon in your DNA, the oxygen you breathe, the calcium in your bones, the iron in your blood, was forged in the nuclear furnaces of stars like Betelgeuse, and not just in the steady burning of those stars, but in their violent deaths. Many of the heaviest elements, gold, silver, platinum, uranium, are created only in the extreme conditions of a supernova or the collision of neutron stars. The gold in your wedding ring, the silver in your jewelry, the rare earth elements in your smartphone, all of it was created in stellar explosions billions of years ago, long before the Earth even existed. You are quite literally made of stardust. This is not metaphor. This is chemistry, cosmology, nuclear physics. The atoms in your left hand may have come from a different star than the atoms in your right hand. You are an assembly of stellar debris, a temporary collection of matter that has cycled through multiple generations of stars, explosions, and planetary formations. Understanding this cycle, how stars form, live, and die, is fundamental to understanding where we came from and how the universe works. But beyond the practical, there's something else. There's a kind of peace that comes from understanding how small we are and how brief. Not a nihilistic peace, not the cold comfort of meaninglessness, but something gentler. A recognition that we are part of something much larger, much older, and much more enduring than ourselves. That the universe has been here long before us and will continue long after we're gone. And that this is not a tragedy. It's simply the nature of things. When you look at Betelgeuse, you're looking at a process that has been unfolding for millions of years, driven by forces so fundamental that they were written into the fabric of reality at the moment of the Big Bang. Gravity, electromagnetism, the nuclear forces that bind atoms together. These are the forces that govern the birth, life, and death of stars. They operated long before humans existed, and they'll continue long after we're gone. You're witnessing a chapter in the story of matter and energy, a story that began nearly 14 billion years ago and will continue in one form or another until the last star fades and the universe grows cold and dark. An event so far in the future that it's almost meaningless to contemplate. And yet, in this moment, you are here to witness it. You, a collection of atoms that briefly became aware of themselves, standing on a rocky planet orbiting an ordinary star, looking out across the void at another star. A star that is dying, slowly, magnificently, inevitably. And understanding, if only faintly, what you are seeing. That feels significant, not because we matter in some cosmic, objective sense. We probably don't. The universe doesn't care about us. It doesn't care about anything. It simply is. But because we have the capacity to understand, to appreciate, to wonder, and that capacity, however fleeting, is worth something. In fact, it might be the only thing that gives the universe meaning at all. Because without consciousness, without minds capable of observing, thinking, feeling, the universe would simply exist, vast and empty and indifferent, with no one to witness its beauty or ponder its mysteries. We are the universe's way of knowing itself, and that's remarkable. Let's return to the science for a moment, because there's more to Betelgeuse than just its eventual fate. One of the most remarkable things about this star is how much we've learned about it in such a short time. For most of history, stars were simply points of light. Even through telescopes, they remained pinpoints, distant, unreachable, fundamentally mysterious. We could measure their brightness, track their positions, note their colors. We could use spectroscopy to determine their chemical composition, their temperature, their motion toward or away from us. But we couldn't see them as objects. We couldn't study their surfaces, their atmospheres, their internal structures. That changed with the advent of modern telescopes and interferometry, a technique that combines the light from multiple telescopes to create images with extraordinary detail. Interferometry works by taking advantage of the wave nature of light. When light waves from two Separate telescopes are combined. They create an interference pattern that contains information about the source's structure. By carefully analyzing this pattern, astronomers can reconstruct an image with a resolution far greater than any single telescope could achieve. Using this technique, astronomers have produced actual images of Betelgeuse's surface, not artists' renditions based on theoretical models, not simulations or approximations. Actual photographs showing the star's disk, its convection cells, its asymmetries, its bright and dark regions. These images revealed something unexpected. Betelgeuse is not a perfect sphere. Its shape is distorted, bulging in some places, flattened in others. The exact reasons for this asymmetry are still being investigated, but likely causes include rapid rotation, though Betelgeuse doesn't seem to be spinning particularly fast. Intense convection currents that create pressure imbalances, or possibly the presence of massive plumes of gas erupting from specific regions of the surface. The surface itself is covered in enormous bright spots, regions where hotter gas is rising from the interior, and vast dark patches where cooler gas is sinking back down. The star is, in essence, boiling. Imagine a pot of water on a stove, heated from below. As the water at the bottom gets hot, it expands, becomes less dense, and rises. The cooler water at the top sinks to take its place. This creates a circular motion called convection. Now imagine that same process, but scaled up to a size where each convection cell is larger than our entire sun, where the temperatures involved are measured in thousands of degrees, where the material rising and falling is ionized plasma, threaded with intense magnetic fields, releasing radiation across the entire electromagnetic spectrum. That's what's happening at Betelgeuse's surface, constantly, chaotically. And this boiling is not gentle. The convection cells on Betelgeuse's surface are so large and so energetic that they can eject massive amounts of material into space. Gas and dust are thrown off the star at speeds of tens of miles per second, forming an extensive atmosphere that extends far beyond the visible surface. This extended atmosphere, or circumstellar envelope, contains material that Betelgeuse has been shedding over thousands or millions of years. Some of this material eventually disperses into the interstellar medium. Some of it cools and condenses into dust grains, which then drift through space, eventually becoming part of new clouds, new stars, new planets. In fact, Betelgeuse is surrounded by nested shells of gas and dust, each one representing a previous episode of mass loss. Telescopes equipped with infrared detectors can see these shells, glowing faintly from the heat of the star. It's a beautiful, complex structure, a star actively shedding its outer layers, preparing, in a sense, for its eventual death. Because when the supernova finally happens, these shells will be swept up and compressed by the expanding shockwave, creating intricate, beautiful structures visible for thousands of years afterward. Supernova remnants are among the most visually stunning objects in the galaxy. The Crab Nebula, the remnant of a supernova that occurred in 1054 AD and was visible from Earth in broad daylight, is still expanding and glowing today, nearly 1,000 years later. Betelgeuse's remnant will be similar. A vast, expanding shell of gas and dust, glowing from the energy of the explosion, slowly mixing with the surrounding interstellar medium, enriching it with the heavy elements created in the star's core. And we'll be able to study it in unprecedented detail, because it will be close, cosmically speaking. Most supernova remnants we study are thousands or tens of thousands of light years away. Betelgeuse is just 650 light years away. That proximity will allow us to observe the remnant's evolution over decades, watching in real time as the shockwave expands, cools, and interacts with the surrounding environment. It will be an extraordinary opportunity for science, a chance to test our models, refine our understanding, and learn things we couldn't possibly learn any other way. We should also talk about scale, because it's almost impossible to truly grasp how large Betelgeuse is without repeatedly, insistently comparing it to things we know. Our Sun has a radius of about 432,000 miles. It's a medium-sized star, neither particularly large nor particularly small. If you could line up Earths side by side across the Sun's diameter, you'd fit about 109 of them. Betelgeuse, depending on where it is in its pulsation cycle, has a radius roughly 700 to 900 times larger than the Sun's. Let that settle for a moment. If you were to replace the Sun with Betelgeuse, placing it at the exact center of our solar system, the star's surface would extend outward to approximately 1.2 to 1.6 astronomical units. That is, 1.2 to 1.6 times the distance from the Sun to Earth. This means Betelgeuse would completely engulf Mercury, whose orbit is at 0.39 astronomical units. It would engulf Venus, whose orbit is at 0.72 astronomical units. It would engulf Earth, whose orbit is at 1.0 astronomical units. The surface of the star would reach approximately the orbit of Mars, at 1.5 astronomical units. And depending on the exact size estimate and the phase of the pulsation cycle, it might even extend to the asteroid belt or beyond. Jupiter, the solar system's largest planet, orbits at 5.2 astronomical units. It would be safe, though it would receive vastly more radiation than it currently does. The night side of Jupiter would glow with the reflected light of a star more than 100,000 times brighter than our Sun. And yet, despite its immense size, Betelgeuse contains only about 15 to 20 times the Sun's mass. How is that possible? The answer is density. Our Sun has an average density of about 1.4 grams per cubic centimeter, slightly denser than water. Most of that mass is concentrated in the core, where densities reach over 150 grams per cubic centimeter. Betelgeuse, by contrast, has an average density of just 0.000001 grams per cubic centimeter. That's about 1/1,000,000th the density of Earth's atmosphere at sea level. The star's outer layers are so tenuous, so diffuse, that they're closer to a vacuum than to anything we'd recognize as solid or even gaseous in the normal sense. And yet, that diffuse gas is so hot, tens of thousands of degrees, that it glows with the brightness of 100,000 suns. This is the paradox of red supergiants. They are simultaneously the largest and the least substantial stars in the universe. Immense, luminous, powerful, and fragile, unstable, nearing collapse. Their cores are dense and hot, fusing heavy elements at a furious rate, but their outer layers are so loosely bound that they're barely held together by gravity. Material is constantly escaping, streaming off into space, forming the complex circumstellar envelopes we can observe with modern telescopes. In a sense, red supergiants like Betelgeuse are transitional objects. They're no longer main sequence stars, burning hydrogen in a stable, equilibrium state. But they're not yet supernovae. They exist in a brief, unstable phase between stability and catastrophe. And we're lucky enough to have one close enough to study in detail. There's a question that often arises when people learn about Betelgeuse's eventual supernova. Should we be worried? It's a reasonable question. After all, we're talking about an explosion that will, for a brief time, outshine an entire galaxy. Surely that must pose some risk. The short answer is no. We're safe. A supernova at a distance of 650 light-years would be spectacular, but not dangerous. The light would be bright, yes, possibly bright enough to read by at night, bright enough to cast shadows, bright enough to be visible during the day. But light alone doesn't harm us. We're bathed in light from the sun every day, and the sun is far closer and, from our perspective, far more intense. The real danger from a supernova comes from radiation. Gamma rays, X-rays, high-energy particles accelerated to nearly the speed of light. When a massive star explodes, it releases a tremendous burst of high-energy radiation. If a planet is close enough to the supernova, this radiation can strip away its atmosphere, destroy its ozone layer, and sterilize its surface. There's some evidence that past mass extinctions on Earth may have been triggered, at least in part, by nearby supernovae. Certain geological layers contain elevated levels of radioactive isotopes that could only have come from a stellar explosion, but these effects drop off rapidly with distance. To pose a serious threat to life on Earth, a supernova would need to occur within about 50 light-years. Ideally much closer, within about 25 light-years, for truly catastrophic effects. Betelgeuse is more than 10 times farther away than that. At 650 light-years, the radiation from Betelgeuse's supernova will reach Earth significantly diluted. By the time the gamma rays and X-rays arrive, they'll have spread out over such a large area that the dose received at Earth will be negligible. Our atmosphere will absorb most of the harmful radiation. The ozone layer will remain intact. Life will continue, blissfully unaware that a star has just died. So when it explodes, we'll get a show. A beautiful, historic, scientifically invaluable show. But we'll be safe. In fact, from a purely observational standpoint, a Betelgeuse supernova would be one of the most important astronomical events in human history. It would give scientists the opportunity to study a supernova in unprecedented detail from a nearby perspective, using instruments far more advanced than anything available during previous naked-eye supernovae. The last time a supernova was visible to the naked eye from Earth was in 1987, when a star in the Large Magellanic Cloud, a satellite galaxy orbiting the Milky Way about 160,000 light-years away, exploded. That event, designated SN 1987A, revolutionized our understanding of stellar death. It was the first time astronomers were able to study a supernova from beginning to end using modern instruments. They detected neutrinos from the collapse of the core, ghostly particles that pass through normal matter almost without interacting, carrying information about the very center of the explosion. They watched the light curve evolve, measuring how the brightness changed over time, comparing it to theoretical models. They observed the remnant as it expanded and cooled, studying the structure of the ejected material, the formation of dust, the interaction with the surrounding gas. And they're still studying it today, more than 35 years later. SN 1987. A continues to provide new insights into how supernovae work, how elements are distributed, and how the energy from an explosion affects its surroundings. But Betelgeuse would be even better. It would be closer, brighter, more accessible to observation. We'd be able to study the supernova across the entire electromagnetic spectrum, from radio waves to gamma rays. We'd be able to watch the shockwave expand through the circumstellar material, compressing and heating the gas that Betelgeuse shed during its life. We'd be able to measure the exact composition of the ejector, determining precisely which elements were created and in what quantities. We'd be able to test our models of core collapse, comparing the observed light curve and spectral evolution to predictions from supercomputer simulations. And we'd be able to study the remnant for centuries, watching it evolve in real time, learning how supernova energy is transferred to the interstellar medium. It would be, in a very real sense, a gift a chance to witness one of the universe's most powerful processes up close, in detail, with all the tools of modern science at our disposal. Let's talk about time again, because it's central to understanding stars and central to understanding our own place in the universe. From a human perspective, Betelgeuse has been there forever. It was there when your great-great-great-grandparents looked up at the winter sky. It was there when Galileo first pointed a telescope at the heavens in 1609, beginning the scientific study of the cosmos. It was there when the pyramids were built in Egypt, when the first cities arose in Mesopotamia, when humans were still nomadic hunter-gatherers, following herds and seasons, telling stories around fires. Go back further. Betelgeuse was there when the first humans migrated out of Africa, spreading across the continents. It was there when our species first evolved, roughly 300,000 years ago. It was there when our ancestors split from other hominins, when the first stone tools were made, when the earliest members of our genus learned to walk upright. In fact, Betelgeuse has been shining for roughly 10 million years. Far, longer than humans or any of our close relatives have existed. But from the star's perspective, human civilization is a flicker. All of recorded history. The rise and fall of empires, the invention of writing, the development of science, the entirety of art and music and philosophy, has occurred during a single, brief phase of Betelgeuse's life, a phase that, in stellar terms, is already ending. If Betelgeuse were a person living an 80-year lifespan, and we scaled its actual age proportionally, then all of human civilization, all of it, from the first cities to the present day, would fit into the last few minutes of that person's life. The invention of agriculture, which happened about 10,000 years ago, would have occurred about 40 seconds ago. The ancient Egyptians who built the pyramids about 4,500 years ago lived 18 seconds ago. The Roman Empire, which dominated the Mediterranean world for centuries, existed about 10 seconds ago. The Renaissance, which transformed European culture and gave birth to modern science, happened 2 seconds ago. Your own lifetime? A fraction of a heartbeat. This is not meant to diminish human experience. Quite the opposite. It's meant to highlight how different our experience of time is from the universe's, and how remarkable it is that we, brief as we are, have managed to figure out what stars are, how they work, and what will happen to them. We've looked at Betelgeuse with telescopes and spectroscopes. We've measured its temperature, its composition, its mass, its distance. We've built computer models that simulate its interior, tracked its pulsations, predicted its future. We've decoded the light it emitted 650 years ago and used that information to reconstruct the life of an object millions of miles across, millions of years old and inconceivably far away. We've done this despite living only a few decades, despite being confined to a single planet, despite having access to only a tiny sliver of the electromagnetic spectrum with our naked eyes. That's extraordinary. And it suggests something quietly profound, that intelligence, however fleeting, is capable of reaching beyond itself. We are small, yes, brief, yes, confined to a tiny corner of a vast universe. But we are not insignificant. We are the universe trying to understand itself. We are matter that has become conscious, aware, capable of looking outward and asking, what is this? Why is it this way? What does it mean? And those questions, however we answer them, are worth asking. There's a certain kind of beauty in impermanence. We tend to think of beauty as something that lasts. Monuments built to endure for centuries, art preserved in museums, ideas passed down through generations. And there's truth to that. Permanence has value. But there's another kind of beauty, one that exists precisely because it's temporary. the beauty of a sunset which lasts only minutes before fading into darkness. The beauty of a flower, blooming, fragile and delicate, destined to wilt within days. The beauty of a snowflake melting on your hand, intricate and unique, vanishing almost as soon as you notice it. These things are beautiful not despite their impermanence, but because of it. Their brevity makes them precious. Their fragility makes them remarkable. Stars in their way are like this. They are not eternal. They are born from clouds of gas and dust, collapsing under gravity, igniting in bursts of fusion. They shine for millions or billions of years, depending on their mass, and then they die, some quietly, fading away into cold darkness, others violently, in explosions that briefly outshine entire galaxies. And their death, far from being a tragedy, is part of what makes them beautiful. Because without stellar death, there would be no heavy elements, no carbon, no oxygen, no iron, no gold. Without stellar death, there would be no rocky planets, no oceans, no atmosphere, no life. The iron in your blood was forged in the core of a dying star. The calcium in your bones was created in a supernova explosion. The oxygen you're breathing right now was produced by fusion in a massive star billions of years ago. Every breath you take is possible because stars have lived and died. In that sense, stellar death is not an ending. It's a transformation, a giving back, a continuation of the cycle that makes the universe interesting, complex, and alive. And Betelgeuse, when it explodes, will contribute to that cycle. Its atoms will scatter into space, spreading outward at thousands of miles per second. Over millions of years, they'll mix with the interstellar medium, mingling with hydrogen and helium left over from the Big Bang, with dust from other dead stars, with the debris of previous generations of stellar evolution. Eventually, gravity will pull some of that material back together. New clouds will form, new stars will ignite, new planets will coalesce, and perhaps, billions of years from now, on one of those planets, something alive will look up at the sky and wonder about the stars. And perhaps in some small way, it will be made of atoms that once belonged to Betelgeuse. That's what death means on a cosmic scale. Not an ending, but a return. Not loss, but transformation. And there's something deeply comforting about that. Let's return one last time to the night sky. Right now, tonight, if the weather is clear and you're far enough from city lights, you can look up and see Betelgeuse. It's there in the upper left of Orion, glowing faintly red. If you're not sure which star it is, look for the 3 bright stars that form Orion's belt. Then trace upward and to the left. The reddish star you see is Betelgeuse. It doesn't look like much. Just another star among thousands, perhaps slightly redder than the others, perhaps slightly dimmer or brighter depending on where it is in its pulsation cycle. But now, you know what it is. You know that it's nearly 1,000 times larger than the Sun, a red supergiant star in the final stages of its life. You know that it's burning through the last of its fuel, fusing heavier and heavier elements in a desperate attempt to hold off gravitational collapse. You know that it's unstable, chaotic, shedding vast amounts of material into space, creating an extensive circumstellar envelope that will one day be swept up and compressed by the shockwave of its own explosion. You know that it's 650 light-years away, which means the light you're seeing left the star in the 14th century, during the late Middle Ages, carrying information about a star that may no longer exist in its current form. You know that it might explode tomorrow or in 100,000 years, and that we have no way of predicting exactly when. And you know that, when it does explode, it will be one of the most spectacular events in human history. a dying star visible in broad daylight, shining with the brightness of the full moon, slowly fading over. Weeks and months until it disappears entirely, leaving behind a neutron star or black hole and a vast expanding cloud of gas and dust. All of that is happening right now in the small red star above Orion's shoulder. And simply knowing that, simply holding that knowledge as you look up, changes the experience of looking. The sky is no longer just a backdrop. It's no longer static or distant. It's alive, dynamic, full of processes unfolding on timescales we can barely imagine, driven by forces we've only recently begun to understand. Stars are being born in vast clouds of gas, collapsing under their own weight, igniting in bursts of fusion. Stars are living, burning steadily for millions or billions of years, converting hydrogen into helium, helium into carbon, carbon into heavier elements. Stars are dying, some quietly, some violently, scattering their atoms into space, enriching the interstellar medium, seeding the next generation of stars and planets. And all of it is happening constantly, invisibly, silently, across the vast expanse of the galaxy. We don't usually think about this. We see the stars as fixed, eternal, unchanging, but they're not. They're temporary, just like us. And you, standing there, looking up, are part of it. You are made of atoms that were forged in the cores of long-dead stars. You are standing on a planet that formed from the debris of stellar explosions. You are breathing oxygen that was created by fusion in massive stars billions of years ago. You are, in the most literal sense, connected to the stars. Not metaphorically, not spiritually, but physically, chemically, atomically. And that connection, however tenuous, however brief, is real. There's a question that often arises in moments like this. What does it all mean? What does it mean that we're made of stardust? What does it mean that the universe is so vast, so old, so indifferent to our existence? What does it mean that stars like Betelgeuse live and die according to immutable physical laws without purpose or intention? And the honest answer is, we don't know. The universe doesn't come with inherent meaning. It simply is. Stars form, burn, and die according to the laws of physics, without asking why. Galaxies collide, planets orbit, life arises and, eventually, ends. None of it means anything in the grand cosmic sense. There is no blueprint, no master plan, no ultimate purpose written into the fabric of reality. The universe is not here for us. It doesn't care about us. It doesn't care about anything. It simply exists, vast and ancient and indifferent, following rules that were set in motion at the moment of the Big Bang and have been operating ever since. But that doesn't make it meaningless, because meaning, as far as we can tell, is something we create. It's a human quality. The ability to look at the universe and find significance, beauty, value, even in things that don't inherently possess those qualities. When you look at Betelgeuse and feel awe, that awe is real. It's not an illusion. It's not a trick of perception. It's a genuine response to something vast and beautiful and strange. The universe didn't give you that sense of awe. You created it, using your capacity for wonder, your ability to contemplate things beyond your immediate experience. When you contemplate the death of a star and feel a sense of peace, or wonder, or humility, that's real too. The universe may not care, but you do, and that's enough. In fact, it's more than enough. It's everything. Because without consciousness, without minds capable of observing, thinking, feeling, the universe would simply exist, vast and empty and indifferent, with no one to witness its beauty or ponder its mysteries. We are the universe's way of knowing itself. We are matter that has become aware, capable of looking outward and inward, asking questions, seeking understanding. And that capacity, however brief, however limited, is extraordinary. We will not live forever. Our species will not endure indefinitely. Even the Earth itself will one day be consumed when the sun becomes a red giant, billions of years from now. But in this moment, we are here. We are aware, we are capable of understanding, at least in part, what the universe is and how it works. And that understanding brings with it a kind of peace. Not because we matter in some objective, cosmic sense. We probably don't. But because we have the ability to see beyond ourselves. To recognize our place in the vast unfolding of cosmic history. To appreciate the beauty of a dying star, even knowing that it will outlive us. That's what Betelgeuse offers every time you look up. A reminder that the universe is larger than us, older than us, stranger than us. A reminder that we are part of something immense, something we're only beginning to understand. A reminder that beauty and meaning are not given to us by the universe, but created by us through our capacity to wonder, to question, to care. So here's what we're left with. Betelgeuse is a red supergiant star, roughly 650 light-years from Earth, nearing the end of its life. It's one of the largest, brightest, and most unstable stars in our night sky. It has been shining for roughly 10 million years, far longer than humans have existed. It has been part of our cultural landscape for as long as we've looked up and told stories about the stars. It's dying. Its core is filling with iron, the element that marks the end of fusion. Soon, in stellar terms, though we can't say when in human terms, that core will collapse. And when it does, Betelgeuse will explode in a supernova, shining briefly with the light of 100 billion suns, visible from Earth even during the day. That explosion could happen in our lifetimes. It could happen in 1,000 years. We don't know. What we do know is that it's coming. And when it happens, we'll witness something that hasn't been seen from Earth in centuries. The death of a star, visible to the naked eye, unfolding in real time. It will be beautiful. It will be historic. It will remind us in the most direct way possible that the universe is not static, not fixed, not eternal. Everything changes. Everything ends, and everything in its own way becomes something else. Betelgeuse will die, but its atoms will live on, scattered through space, becoming part of new stars, new worlds, new stories. And we, brief as we are, will have been here to witness it. Small, yes. Fleeting, yes. Insignificant in the grand cosmic scheme, but here, aware, capable of wonder. And for as long as we exist, that will be enough. Before we close, there are a few more layers to this story worth exploring. Because Betelgeuse isn't just a star waiting to explode. It's a window into processes we're still working to understand, a laboratory for physics we can barely replicate on Earth, and a reminder of mysteries that remain unsolved. Let's dig deeper into what makes Betelgeuse truly extraordinary. Let's trace back through time and explore how humanity's understanding of Betelgeuse has evolved, because this history is itself a story of discovery, wonder, and the gradual unveiling of cosmic truth. For most of human history, Betelgeuse was simply a star. A bright point of reddish light in the winter sky, part of a constellation that appeared and disappeared with the seasons. Ancient observers noticed it, they named it, they wove it into their stories. The Egyptians associated Orion with Osiris, god of the afterlife. They aligned their pyramids with Orion's belt, creating a connection between earth and sky, between the mortal and the eternal. The Greeks saw Orion as a hunter, placed in the sky by Zeus. Different versions of the myth offer different explanations. Some say he was killed by a scorpion, which is why Orion sets as Scorpius rises. Others say he was struck down for his arrogance or his attempted assault on the goddess Artemis. But in all these stories, the constellation was seen as a pattern, a shape, a figure, a meaningful arrangement of stars. No one asked what the stars themselves were made of. No one wondered how far away they might be. No one conceived that they might be anything other than small lights affixed to the celestial sphere. This began to change in the Renaissance. In 1609, Galileo turned his telescope to the heavens and discovered that the universe was far more complex than anyone had imagined. The moon had mountains and craters. Jupiter had moons. The Milky Way was composed of countless individual stars. But stars themselves remained mysterious. Even through the best telescopes, they appeared as dimensionless points of light. Their true nature remained unknown. Were they small, nearby objects, or vast, distant suns like our own? How hot were they? What were they made of? How far away were they? These questions would take centuries to answer. In the 19th century, astronomers began to make progress. They measured the distances to nearby stars using parallax, the apparent shift in a star's position as Earth orbits the Sun. This revealed that stars were incredibly far away, far more distant than anyone had imagined. They also began to study starlight using spectroscopy, passing light through a prism to break it into its component colors, revealing dark lines that corresponded to specific chemical elements. This was revolutionary. For the first time, astronomers could determine what stars were made of without ever visiting them. They could measure temperatures, compositions, motions, and Betelgeuse began to reveal its secrets. Astronomers noticed that its spectrum was different from most stars. It showed strong absorption lines corresponding to molecules, compounds that could only exist at relatively cool temperatures. This suggested that Betelgeuse was a red star, cooler than the Sun, but far more luminous, which meant it had to be enormous. In the early 20th century, astronomers began to work out the relationship between a star's color, brightness, and size. They developed the Hertzsprung-Russell diagram, a tool that plotted stars according to their temperature and luminosity, revealing distinct populations: main sequence stars, giants, supergiants, white dwarfs. Betelgeuse fell squarely in the supergiant region. But just how large was it? In 1920, Albert Michelson and Francis Pease used a technique called interferometry to measure the angular diameter of Betelgeuse for the first time. They found that the star had a measurable disk. It wasn't just a point of light, but an actual extended object. This was the first time anyone had measured the size of a star other than the Sun. Their measurements suggested that Betelgeuse was roughly 300 times larger than the Sun. Already an astonishing size, though later, more precise measurements would show it was even larger. This was a turning point. Betelgeuse wasn't just a bright star, it was a monster. An object so large that it defied comprehension. And as the 20th century progressed, astronomers learned more and more. They discovered that Betelgeuse was variable. Its brightness changed over time, pulsing irregularly on timescales of months to years. They measured its distance using parallax and other techniques, refining their estimates from tens of light years to hundreds. They studied its spectrum in detail, identifying the elements present in its atmosphere, measuring its radial velocity, tracking its motion through space. They used infrared telescopes to peer through the dust and see the star's extended envelope, the shells of gas and dust it had shed over millennia. And they began to understand what Betelgeuse was: a massive star in the final stages of its life, approaching the moment when its core would collapse and it would explode in a supernova. This understanding represents one of humanity's great intellectual achievements, the ability to look at a point of light in the sky and deduce its past, its present, and its future, using nothing but physics, mathematics, and careful observation. We went from seeing Betelgeuse as a fixed point on the celestial sphere to understanding it as a dynamic, evolving object. A star with a history, a personality, a fate. And we did this without ever getting close to it, without ever touching it, using only light, photons that left the star 650 years ago and traveled across the void to reach our eyes, our telescopes, our instruments. That's the power of science. That's the beauty of astronomy. We're landlocked on this small planet, but we're not blind. We can reach out across space and time, gathering information, building models, understanding the universe in ways that would have seemed like magic to our ancestors. And Betelgeuse has been a teacher throughout this journey, a bright, nearby, accessible object that has helped us refine our techniques, test our theories, and expand our understanding of how stars live and die. Let's return to a question we touched on earlier. Does Betelgeuse have companions? This isn't just idle curiosity. The answer could fundamentally change how we understand the star's evolution and eventual fate. Most massive stars are members of binary or multiple star systems. In fact, studies suggest that more than 70% of massive stars have at least one companion. Sometimes another massive star, sometimes a smaller star, sometimes multiple companions in complex gravitational dances. Binary systems evolve differently than single stars. The two stars can interact gravitationally, exchanging mass, altering each other's rotation, even merging in some cases. If Betelgeuse has a companion, it might be hidden in the star's glare, too faint to see directly, but detectable through its gravitational influence. Astronomers have looked for signs of such a companion. They've analyzed Betelgeuse's motion through space, looking for wobbles that might indicate an unseen partner. They've studied its spectrum, looking for Doppler shifts that might reveal orbital motion. So far, the evidence is inconclusive. Some studies have reported possible detections, slight asymmetries in the star's light curve, or irregularities in its proper motion. But these could also be explained by other factors like the star's pulsations or its complex surface structure. Other studies have found no convincing evidence of a companion, suggesting that Betelgeuse might be alone. The truth is, we don't know yet. And what about planets? Could Betelgeuse have a planetary system? This is an even more challenging question. Detecting planets around other stars is difficult enough when the star is stable and relatively small. Around a pulsating red supergiant like Betelgeuse, it's nearly impossible with current technology. But let's think about the possibilities. Betelgeuse formed from a collapsing cloud of gas and dust just like every other star. That cloud likely had a rotating disk around it from which planets could have formed. So it's possible that Betelgeuse once had planets. But would they have survived? When Betelgeuse was a young main sequence star, similar to massive stars we see today, it would have been far smaller and hotter than it is now. Planets could have formed in stable orbits, perhaps ranging from a few astronomical units out to tens or hundreds of astronomical units. But as Betelgeuse evolved and expanded into a red supergiant, it would have engulfed any planets in close orbits. Mercury-like and Venus-like worlds would have been consumed, vaporized in the star's expanding envelope. Earth-like planets at one astronomical unit would have been destroyed. Mars-like planets might have survived if they were far enough out, perhaps barely escaping the star's expansion. And more distant planets, Jupiter-like gas giants or icy worlds in the outer regions, might have survived intact, though they would now be bathed in intense radiation and bombarded by stellar wind. If such planets exist, they would be experiencing something unprecedented. Their parent star, once a steady, reliable source of light and warmth, has transformed into an unstable giant that dominates the sky, pulsing, shedding material, approaching its final violent end. What would it be like to watch from such a planet? Imagine a world orbiting 20 astronomical units from Betelgeuse, roughly the distance of Uranus from our Sun. From that vantage point, Betelgeuse would appear roughly 40 to 50 times larger than the Sun appears from Earth, covering a significant portion of the sky. The light would be dim, reddish, flickering as the star pulsates. Shadows would be soft and diffuse. The temperature on the planet's surface would fluctuate as the star brightened and dimmed. And overhead, you'd see storms on the star's surface. Vast convection cells rising and sinking, dark spots appearing and disappearing, enormous plumes of gas erupting into space. It would be beautiful, terrifying, apocalyptic. And then, one day, the star would explode. Even at 20 astronomical units, the explosion would be catastrophic. The sudden burst of light and radiation would heat the planet's atmosphere to thousands of degrees. Any ice would vaporize. Any atmosphere would be stripped away. The surface would be sterilized. And then, the shockwave would arrive. A wall of high-speed ejecta traveling at thousands of miles per second, slamming into the planet with enough force to potentially shatter it entirely. If the planet survived, it would be left in orbit around a tiny, dense remnant, a neutron star or black hole, in a system that bore no resemblance to the one it once knew. Of course, this is all speculation. We have no evidence that such planets exist, but the possibility is there, and it's a reminder that supernovae don't just affect stars. They affect entire systems, reshaping or destroying everything in their vicinity. One of the most puzzling aspects of red supergiant stars is how they lose so much mass toward the end of their lives. Betelgeuse is currently shedding material at an astonishing rate. Astronomers estimate that the star loses roughly the mass of Earth every 400 to 500 years. That might not sound like much. After all, Earth is tiny compared to a star, but over the course of Betelgeuse's lifetime, this adds up to a significant fraction of the star's total mass. The star may have started its life with 20 or 25 solar masses. Today, it has roughly 15 to 20. Where did the rest go? It was blown away, carried off by stellar winds, streams of charged particles flowing outward from the star's surface, driven by radiation pressure and convection. These winds aren't gentle. They move at speeds of tens of miles per second, carrying gas and dust far beyond the star's visible surface, creating the extensive circumstellar envelope we can detect with infrared telescopes. But here's the mystery. We don't fully understand how this happens. The physics of stellar winds in red supergiants is complex, and our current models struggle to explain the observed mass loss rates. Radiation pressure alone, the outward force exerted by photons as they stream from the star's surface, doesn't seem to be enough. There must be other mechanisms at play, perhaps magnetic fields which can accelerate charged particles, perhaps shock waves from pulsations which can lift material off the surface, perhaps convection cells so powerful they literally throw gas into space, or perhaps some combination of all three. This is cutting-edge research. Scientists are still working to understand exactly how red supergiants shed their outer layers, and Betelgeuse is one of the best-studied examples we have. The 2019 to 2020 dimming event provided new clues. By studying how the ejected material cooled and condensed, astronomers gained insights into the temperature, density, and composition of the gas being shed by the star. But questions remain. Why did Betelgeuse eject that particular cloud at that particular time? Was it a random fluctuation, or was it triggered by some deeper instability in the star's interior? We don't know yet, and that's part of what makes Betelgeuse so valuable scientifically. It's close enough that we can study it in detail, unstable enough that it shows us dramatic changes, and mysterious enough that it continues to surprise us. Every observation adds to our understanding. Every measurement refines our models. Every new piece of data brings us closer to answering fundamental questions about how massive stars evolve and die. Let's zoom inward for a moment into the heart of Betelgeuse, where the real drama is unfolding. The star's interior is nothing like our sun's. Our sun has a relatively simple structure. At the center is a core where hydrogen fuses into helium, releasing energy. That energy radiates outward, gradually making its way to the surface over the course of hundreds of thousands of years. The outer third of the sun is convective. Hot gas rises, cools, and sinks back down. But the inner two-thirds are stable, with energy transported primarily by radiation. Betelgeuse is far more chaotic. The core is a layered structure like an onion, with different fusion processes happening at different depths. At the very center, silicon is fusing into iron. This is the final stage of fusion, and it's happening fast, consuming the silicon in a matter of days or weeks. Just outside the core, there's a shell where oxygen is fusing into heavier elements. Outside that, a shell where neon is fusing. Outside that, carbon, then helium. Then, in the outermost layers, whatever hydrogen remains. Each shell burns at a different temperature, a different rate, producing different elements. The energy output is irregular, pulsing as the various shells expand and contract, interact and interfere with one another. And above all this, the star's enormous convective envelope churns and boils, carrying material from deep inside the star to the surface and back again. This convection is so powerful, so energetic, that it can actually dredge up material from the fusion shells below, bringing freshly synthesized elements to the surface where they can be ejected into space. In fact, astronomers have detected unusual abundances of certain elements in Betelgeuse's spectrum, elements that shouldn't be present at the surface in such quantities unless convection is mixing the star's interior. This process, called convective dredge-up, is one of the ways stars enrich their surroundings with heavy elements even before they explode. It's messy, it's chaotic, it's nothing like the orderly, predictable fusion happening in the sun. And it's this very chaos that makes red supergiants so hard to model. Computer simulations of stellar interiors require enormous computational power. You have to solve complex equations describing how gas behaves under extreme temperatures and pressures, how radiation interacts with matter, how energy is transported from the core to the surface. For a stable star like the Sun, this is manageable. The physics is well understood and the star's behavior is predictable. For a star like Betelgeuse, it's far more difficult. The pulsations are irregular, the convection is turbulent, the mass loss is unpredictable. And all of these processes interact with each other in ways that are hard to calculate. Even with modern supercomputers, our simulations of red supergiants are approximate at best. We can capture the general behavior, but the details often elude us. That's why observations are so important. By watching Betelgeuse closely, by measuring its brightness, its spectrum, its size, we can test our models and refine them, gradually improving our understanding of how these stars work. Here's another mystery. Is Betelgeuse rotating? And if so, how fast? This might seem like a simple question, but it's surprisingly hard to answer. For most stars, we can measure rotation by looking at the Doppler shift in their spectral lines. As the star rotates, one side moves toward us and the other moves away, causing the light to be slightly blue-shifted on one side and red-shifted on the other. This creates a characteristic broadening of the spectral lines that we can measure. But for red supergiants like Betelgeuse, this technique is complicated by the star's enormous size and turbulent atmosphere. The convection cells are so large and move so fast that they create their own Doppler shifts, which can mask or mimic the signal from rotation. Current estimates suggest that Betelgeuse is rotating slowly, perhaps 5 to 10 miles per second at the equator, which is extremely slow for a star of this size. At that rate, it would take roughly 20 to 30 years for the star to complete one rotation. By comparison, our Sun rotates at about 4,500 miles per hour at its equator and completes one rotation in about 25 days. So Betelgeuse is rotating, but barely. This raises an interesting question. Why? Stars are born from rotating clouds of gas. As the cloud collapses, conservation of angular momentum causes it to spin faster, much like a figure skater pulling in their arms. Young stars tend to rotate rapidly, but as they age, they lose angular momentum through various processes: stellar winds, magnetic braking, mass loss. By the time a star becomes a red supergiant, it has typically slowed down considerably. But the details of this process are still being worked out. And here's where it gets even more interesting. Betelgeuse's slow rotation might actually influence its eventual supernova. Some models suggest that rotation can affect how a massive star's core collapses. A rapidly rotating core might form a different kind of remnant, or might produce an asymmetric explosion. Betelgeuse's slow rotation suggests that its supernova will likely be relatively symmetric, a more or less spherical explosion, rather than the highly asymmetric, jet-driven explosions we sometimes see in other supernovae. But again, this is an area of active research. We won't know for sure until the supernova actually happens. There's another intriguing possibility worth discussing. Does Betelgeuse have a companion star? For many years, astronomers have debated whether Betelgeuse is actually a binary system. Two stars orbiting a common center of mass, rather than a single isolated star. The evidence is mixed. Some observations suggest irregularities in Betelgeuse's motion that could be explained by the gravitational influence of an unseen companion. Other observations show asymmetries in the star's brightness and shape that might result from tidal interactions with a nearby star. But no companion has ever been definitively detected. If Betelgeuse does have a companion, it would have to be much smaller and dimmer. Perhaps a white dwarf or a main sequence star that's completely overwhelmed by Betelgeuse's brilliant light. And here's why this matters. If Betelgeuse is in a binary system, the presence of a companion could affect both the star's evolution and its eventual supernova. A companion could strip away some of Betelgeuse's outer layers, altering the mass loss rate. It could tidally interact with the supergiant, affecting its rotation and pulsations. And if the companion is close enough, it might even survive the supernova, becoming a runaway star ejected from the system at high velocity. Some of the most energetic and unusual supernovae we've observed appear to involve binary systems, where the interaction between two stars creates exotic outcomes. Could Betelgeuse's supernova be one of these unusual events? Possibly. But without detecting a companion, we can't be sure. It's worth noting that many massive stars are members of binary or multiple star systems. In fact, it's estimated that the majority of massive stars have at least one companion. So it wouldn't be surprising if Betelgeuse turned out to be a binary. But for now, it remains an open question. one of many mysteries surrounding this enigmatic star. Let's engage in a thought experiment. If Betelgeuse had planets, what would happen to them when the star goes supernova? We have no evidence that Betelgeuse has planets. The star's intense radiation and powerful stellar winds would make planet formation and survival extremely challenging. Any planets that did form would have to orbit at great distances to avoid being destroyed. But let's imagine for a moment that there is a planet, perhaps a gas giant or a rocky world, orbiting at a safe distance, far enough to avoid the worst of the star's heat and wind. What would life be like on such a world? First, the sky would be dominated by Betelgeuse. Even from a safe orbital distance, say 10 or 20 astronomical units, the star would appear enormous, filling a significant portion of the sky. It wouldn't be a point of light like our sun appears from Earth. It would be a visible disk, glowing, red, mottled with dark spots and bright regions. The light would be dimmer than sunlight on Earth, but the star's sheer size would make up for its cooler temperature. Depending on the exact distance, the planet might receive a similar amount of energy to what Earth receives from the sun. But there would be differences. The light would be redder, shifted toward longer wavelengths. Plants, if they existed, might have evolved to photosynthesize using red and infrared light, rather than the visible spectrum we're used to. The star would pulsate visibly, growing brighter and dimmer over weeks or months. Seasons wouldn't be determined by the planet's axial tilt, but by the star's irregular variations. And then, one day, without warning, the star would explode. The first sign would be a sudden, dramatic increase in brightness. Within hours, Betelgeuse would become hundreds of times brighter than normal, flooding the planet with intense radiation. If the planet had an atmosphere, the outer layers would begin to heat up, possibly even being stripped away by the sudden influx of energy. Then, over the following days and weeks, the shock wave would arrive. A wall of high-energy particles and gas traveling at thousands of miles per second. If the planet was close enough, within a few astronomical units, it would be vaporized almost instantly, torn apart by the sheer force of the explosion. If it was farther away, 10, 20, 50 astronomical units, it might survive but heavily damaged. The atmosphere would be stripped away, the surface would be sterilized by radiation, any oceans would boil away. Eventually, the shockwave would pass, and the planet would be left orbiting a neutron star or black hole, a tiny, dense remnant of the star that once dominated its sky. The night would be truly dark for the first time. The red glow that illuminated everything would be gone, replaced by the faint, cold light of distant stars. Of course, this is all speculative. We don't know if Betelgeuse has planets. We don't know exactly how close they'd need to be to survive. We don't even know for certain what kind of remnant Betelgeuse will leave behind. But it's a reminder that supernovae don't just affect the dying star. They reshape entire stellar systems, destroying some worlds and transforming others. And in the grander scheme, they also create the conditions for new worlds to form, scattering heavy elements into space, triggering the collapse of nearby gas clouds, seeding the next generation of stars and planets. Let's return to Earth and think about what Betelgeuse's supernova would mean for us, not scientifically, but culturally. Throughout human history, celestial events have been interpreted as omens, signs, messages from the gods. Comets, eclipses, meteor showers. All have been seen as significant, portentous, meaningful. A supernova visible in the daytime sky would be unlike anything in living memory. The last supernova visible to the naked eye was in 1987, but it was only visible from the southern hemisphere and never became bright enough to see during the day. Before that, you'd have to go back to 1604, Kepler's supernova, observed by Johannes Kepler and other astronomers of the time. And before that, 1572, Tycho's supernova, observed by Tycho Brahe, which challenged the Aristotelian belief that the heavens were unchanging. These events had profound impacts on astronomy and philosophy. They demonstrated that the cosmos was not static, not perfect, not eternal. They helped pave the way for the scientific revolution, but they occurred in pre-modern times, before mass media, before global communication, before the internet. A Betelgeuse supernova would occur in the age of social media, instant global communication, and widespread scientific literacy. It would trend on every platform. It would dominate news cycles for weeks. Scientists would give interviews explaining what was happening and why. Telescopes would be booked solid. Every astronomer on the planet scrambling to collect data. There would be misinformation, of course. Conspiracy theories, claims that the supernova was a sign of the end times, or proof of alien intervention, or evidence of some cosmic catastrophe. But there would also be wonder, curiosity, a shared global experience of witnessing something truly extraordinary. People would gather in parks and on rooftops, looking up at the bright new star that had appeared seemingly overnight. Parents would point it out to their children. Artists would paint it. Poets would write about it. For a few weeks, the entire world would be reminded that we live in a universe far larger, far stranger, and far more dynamic than we usually remember. And perhaps that shared experience would be valuable in its own right. A reminder of our common humanity, our shared home on this small planet, our collective place in the cosmos. One of the most frustrating aspects of Betelgeuse is that we can't predict when it will explode. We know it's coming. We know it's soon in astronomical terms. But we don't know if soon means tomorrow or 100,000 years from now. Why is this so hard to predict? The problem is that the final stages of a massive star's life are chaotic and hard to model. The core is fusing heavier and heavier elements, each stage happening faster than the last. The star is pulsating irregularly. It's shedding mass unpredictably. And the moment of core collapse, when fusion finally stops and gravity takes over, is determined by processes happening deep inside the star, far beyond our ability to observe directly. We can't see the core. We can only see the surface. And the surface doesn't always reflect what's happening inside. It's like trying to predict an earthquake. We know earthquakes happen when stress builds up along fault lines. We know roughly where they're likely to occur. But we can't predict exactly when the next one will happen, because the conditions deep underground are hidden from us. Similarly, we know Betelgeuse will go supernova when its core fills with iron and collapses. We know this will happen eventually, but the exact timing depends on details we can't measure. The precise rate of fusion, the exact mass of the core, the structure of the shells around it. Some scientists are working on ways to detect the early warning signs of an impending supernova. One promising avenue is neutrino detection. Neutrinos are ghostly particles produced in enormous quantities during the final hours before a core collapse. They escape the star almost immediately, unlike light, which can take thousands of years to work its way out from the core. If we could detect a sudden spike in neutrinos coming from Betelgeuse, we'd know the supernova was about to happen, possibly hours before the light reaches us. Several neutrino observatories around the world are constantly monitoring the sky for such signals. If Betelgeuse's core collapses, they should detect it. But neutrinos are extremely hard to detect. They pass through normal matter almost without interacting. You'd need a massive detector deep underground to shield it from cosmic rays, and even then, you'd only catch a tiny fraction of the neutrinos passing through. Still, it's possible. In 1987, when SN 1987A exploded, neutrino detectors in Japan and the United States registered a burst of about 20 neutrinos over the course of a few seconds. An incredibly small number, but enough to confirm that the core had collapsed. If Betelgeuse goes supernova, we should detect far more neutrinos, because it's much closer. And that would give us a few precious hours of warning. Time to point every available telescope at Orion. Time to alert astronomers around the world. Time to prepare for one of the most important observational campaigns in history. But until that moment comes, we wait. We watch, we measure, and we wonder. There's another fascinating aspect to studying Betelgeuse. It helps us understand the history of our own galaxy. Every star that explodes in a supernova leaves behind not just a remnant, but also a signature, a pattern of elements, isotopes, and chemical abundances that can tell us about the conditions under which the star formed and died. By studying the composition of stars and gas clouds throughout the Milky Way, astronomers can reconstruct the galaxy's history. When different generations of stars formed, how they evolved, and how they enriched the interstellar medium with heavy elements. This is sometimes called stellar archaeology or galactic archaeology, using the chemical composition of stars to reconstruct the past. And Betelgeuse is a valuable piece of that puzzle. Its spectrum tells us what elements are present in its atmosphere and in what quantities. By comparing this to theoretical models, we can infer what kind of gas cloud it formed from, and therefore what previous generations of stars had enriched that cloud. Betelgeuse formed roughly 8 to 10 million years ago from a cloud that had already been enriched with heavy elements by earlier generations of stars. It's not a first-generation star. Those would have been made of almost pure hydrogen and helium, with virtually no heavy elements. Instead, Betelgeuse is probably a second or third generation star formed from material that had already cycled through previous stellar lifetimes. And when Betelgeuse explodes, it will add its own contribution to the interstellar medium. A fresh injection of oxygen, carbon, silicon, iron, and heavier elements, enriching the gas clouds from which future stars will form. In this way, each generation of stars builds on the previous one, gradually increasing the galaxy's overall metal content. In astronomy, a metal is any element heavier than hydrogen and helium. This process has been happening for billions of years, and it's still happening today. The Sun formed about 4.5 billion years ago from a cloud that had already been enriched by countless previous generations of stars. The Earth condensed from that same material, and life on Earth is made from atoms that have been through multiple stellar cycles. Forged in the cores of ancient stars, scattered by supernova explosions, collected into new clouds, incorporated into new stars and planets, and eventually assembled into you. When you look at Betelgeuse, you're not just seeing a star, you're seeing a link in a chain that connects you to the deep history of the galaxy, to processes that have been unfolding for billions of years, to a cycle of creation and destruction that will continue long after we're gone. Let's step back for a moment and think about time itself. One of the most challenging aspects of understanding stars is wrapping your mind around the timescales involved. Human experience operates on timescales of seconds, minutes, hours, days, years. We can intuitively grasp these durations. We can imagine them, plan around them, remember them. But stellar timescales are different. Betelgeuse has been shining for 10 million years. That's a number so large it becomes almost meaningless. How do you conceive of 10 million years? If you counted one number per second, it would take you roughly 300 years just to count to 10 million. And that's just counting, not experiencing, not living through. 10 million years ago, our ancestors were small, ape-like creatures living in trees. The entire span of human civilization, from the first cities to the present day, is less than 0.001% of Betelgeuse's lifetime. And yet, to the star, 10 million years is just a life. It was born, it lived, and it will die, all on a timescale that feels natural from a stellar perspective. This is what scientists call deep time. Time on geological or cosmological scales, far beyond human experience. Understanding deep time requires a kind of mental shift. You have to stop thinking in terms of human lifespans and start thinking in terms of processes. Slow, gradual changes that accumulate over millions or billions of years. Continental drift, evolution, the formation of mountain ranges, the collision of galaxies. These processes are invisible on human timescales, but they're real, they're powerful, and they shape the universe we live in. And there's something humbling about this. It's easy to feel like we're the center of the universe. Our concerns, our problems, our achievements, they loom large in our own minds. But when you step back and look at deep time, you realize how brief we are, how small, how temporary. And yet, paradoxically, this realization doesn't diminish us. Instead, it puts things in perspective. The fact that we exist at all in this brief window of time on this small planet in this vast universe, that's extraordinary. The fact that we can look up at Betelgeuse and understand what it is, how it works, what will happen to it. That's remarkable. We are small and brief, yes, but we're also capable of comprehending things far larger and older than ourselves. We can hold deep time in our minds, even if we can't truly experience it. And that capacity, the ability to think beyond our own immediate experience, to understand processes that unfold over millions of years, to see ourselves as part of a much larger story. That's something worth celebrating. We talked earlier about the beauty of impermanence. Let's return to that idea one more time because it's central to understanding not just Betelgeuse, but our own place in the universe. There's a Japanese concept called mono no aware, a sensitivity to the ephemeral nature of things. It's the bittersweet awareness that everything is temporary, that beauty is fleeting, and that this very transience is what makes things beautiful. Cherry blossoms are beautiful precisely because they last only a few days. A sunset is precious because it fades into night. A moment of joy is meaningful because it will end. Stars are like this too. They're not eternal. They're temporary structures held together by gravity, powered by fusion, destined to run out of fuel and collapse. But this doesn't make them less beautiful. If anything, it makes them more so. Betelgeuse will explode, its light will fade, the constellation Orion will be forever changed. And that's okay. In fact, it's more than okay. It's part of the natural order of things. Nothing lasts forever. Not stars, not planets, not galaxies, not even the universe itself will last forever. Eventually, in the unimaginably distant future, the last stars will fade, and the universe will grow cold and dark. But that doesn't make the present moment meaningless. It makes it precious. We're here now. We're alive now. We can see Betelgeuse now. And one day, we won't be. One day, Betelgeuse won't be. But in this moment, we exist together, a star and a species separated by 650 light years, connected by light, by curiosity, by the simple act of looking up and wondering. That connection is real, even if it's brief. It matters, even if it's temporary. And there's a kind of peace in accepting that. Not a resignation, not a giving up, but an acceptance that everything changes, everything ends, and that's okay. because change is how the universe works. Death is how the universe transforms, and transformation is how the universe stays interesting, complex, alive. Betelgeuse will die. But in dying, it will give birth to new stars, new worlds, possibly new life. We will die, but in dying, we return our atoms to the earth, to the cycle of life, to the ongoing story of matter and energy. Nothing is lost. Everything is transformed. And that transformation, that endless cycling of matter through different forms, star to planet to life to death to new stars, that's the real story of the universe. We're all part of it. All of us. Every atom, every star, every moment. And for as long as we're here, we get to witness it. That's the gift. Before we conclude, let's take a moment to look back at the supernovae humanity has witnessed throughout recorded history. Because when Betelgeuse explodes, it won't be the first time humans have seen such an event. But it will almost certainly be the most observed, the most studied, and the most widely shared. The earliest recorded supernova observation dates back to 185 AD, documented by Chinese astronomers who described a guest star that appeared in the sky and remained visible for about 8 months. We now know this was almost certainly a supernova, though we haven't definitively identified the remnant. In 1006 AD, a supernova appeared that was so bright it cast shadows at night. Records from China, Japan, Europe, the Arab world, and possibly North America all describe this spectacular event. At its peak, it may have been as bright as a quarter moon, bright enough to read by. It was visible for years before fading from sight. The remnant of this supernova, SN 1006, is still visible today through telescopes. An expanding shell of gas glowing from the energy of the explosion that occurred more than 1,000 years ago. Then came SN 1054, the supernova that created the Crab Nebula. Chinese and Arab astronomers recorded its appearance in incredible detail. It was visible during the day for 23 days and remained visible at night for nearly 2 years. This supernova left behind not just a nebula but also a pulsar, a rapidly spinning neutron star that emits beams of radiation like a cosmic lighthouse, flashing 30 times per second. In 1572, Tycho Brahe observed a supernova that appeared in the constellation Cassiopeia. This event was so significant that it's often called Tycho's supernova, or stellar nova, the new star. Tycho's careful observations of this supernova helped challenge the prevailing Aristotelian view that the heavens were perfect and unchanging. If a new star could appear, the heavens must be mutable, dynamic, subject to change. This was a revolutionary idea. It helped pave the way for the scientific revolution that would follow. Just 32 years later, in 1604, Johannes Kepler observed another supernova, also in our galaxy. This would be the last supernova visible to the naked eye in the Milky Way, at least so far. Since then, nothing. We've detected supernova in other galaxies, thousands of them using modern telescopes, but none in our own galaxy visible to the naked eye. The most recent naked eye supernova was SN 1987A in the Large Magellanic Cloud, a satellite galaxy of the Milky Way. This was a watershed moment for astronomy. The first supernova close enough and bright enough to study in detail with modern instruments. Neutrino detectors registered the collapse of the core. Spectroscopy revealed the composition of the ejecta. Telescopes tracked the evolution of the light curve, the formation of the remnant, the interaction with surrounding gas. We're still studying SN 1987. A today, more than 35 years later. It continues to teach us about the physics of stellar explosions, but SN 1987A was in another galaxy, 160,000 light-years away. It was bright, but not spectacular, visible to the naked eye, but only barely, and only from the southern hemisphere. Betelgeuse will be different. At 650 light-years away, it's roughly 250 times closer than SN 1987A. And that makes an enormous difference. Brightness falls off with the square of distance. Something twice as far away appears 4 times dimmer. Something 10 times farther away appears 100 times dimmer. By that calculation, Betelgeuse's supernova should appear roughly 60,000 times brighter than SN 1987A. SN 1987A peaked at apparent magnitude 2.9, about as bright as the stars in the Big Dipper, easily visible but not spectacular. Betelgeuse, at 60,000 times brighter, would peak at apparent magnitude -12.4, roughly as bright as the full moon. For a few days, Orion would have 2 brilliant lights: Rigel, the blue supergiant that forms the Hunter's Foot, and Betelgeuse, transformed into something far brighter, far stranger. You'd be able to see it during the day. You'd be able to read by its light at night. It would cast shadows. It would dominate the sky. And unlike previous supernovae, which were observed by a relative handful of astronomers and chroniclers, Betelgeuse's supernova would be instantly visible to billions of people. Within minutes, social media would explode with posts, photos, videos. News organizations would scramble to explain what was happening. Scientists would give interviews, providing context and reassurance. The entire world would be watching. For a few weeks, we'd be united in wonder, looking up at the same sky, witnessing the same cosmic event, sharing in the same sense of awe. And then, gradually, it would fade. The light would dim. The brightness would decrease. Within months, you'd need binoculars to see it. Within a year, you'd need a telescope. But the experience would remain. The memory would endure. An entire generation would remember where they were when Betelgeuse exploded. It would become a cultural touchstone, a moment of shared history. Do you remember the supernova? People would ask, decades later. And the answer would be yes. Let's paint a more detailed picture of what Betelgeuse's supernova will actually look like from Earth, because the visual experience will be unlike anything most people alive today have ever seen. The first hint will likely come from astronomers. If we're lucky, neutrino detectors will register a burst of particles hours before the light reaches us, giving us advance warning. Scientists will send out alerts. Observatories will prepare, or it might happen without warning. Someone looking up at Orion might notice that Betelgeuse seems brighter than usual. Others might confirm it, and within hours the news would spread. In the first day, Betelgeuse will brighten rapidly. It will go from magnitude 0.5, its current average brightness, to magnitude -8 or -10, becoming one of the brightest objects in the night sky, far brighter than any star, brighter than any planet except Venus at its brightest. The color will change. Betelgeuse is normally reddish-orange, but as the supernova develops, it will become white or even slightly bluish-white as the temperature of the expanding ejecta increases. By the second or third day, it will reach its peak brightness, possibly magnitude -12, as bright as the full moon. At this point, it will be visible during the day, appearing as a bright point of light in the sky even when the sun is up. At night, it will be spectacular. It will cast distinct shadows. You'll be able to see your hand by its light. The landscape will be bathed in a dim, eerie glow. Not enough to see colors clearly, but enough to navigate without a flashlight. Orion will be transformed. instead of the familiar hourglass shape with two bright stars marking the shoulders. There will be one brilliant beacon and Rigel, much dimmer by comparison. The appearance will remain more or less constant for several days. Then, slowly, it will begin to fade. After a week, it might dim to magnitude -8. Still bright, brighter than Venus, but no longer overwhelming. After 2 weeks, magnitude -5. Still easily visible during the day, still dramatically bright at night. After a month, magnitude 0 or -1. Still one of the brightest stars in the sky, but no longer extraordinary. After 3 months, magnitude +3 or +4. You'd need binoculars to see it comfortably. After a year, magnitude +8 or +10. Telescope only. And then it would continue fading, slowly, over years and decades, as the supernova remnant expanded and cooled. The exact details would depend on the type of supernova, the viewing angle, and various other factors. But this gives you a general sense of the timeline. The entire spectacle would last roughly 3 to 6 months for casual observers. After that, you'd need optical aids to see it. But during those months, the sky would be different. Orion would be different. The night would be different. And people around the world would look up and remember that we live in a dynamic, changing universe where even the stars are temporary. After the initial excitement fades, after the light dims and Betelgeuse disappears from the naked eye sky, the real scientific work will begin. Because the supernova remnant, the expanding shell of gas and dust left behind, will be a treasure trove of information, visible and accessible for centuries. Astronomers will study it with every available instrument. Radio telescopes will map its structure, tracing the shock waves as they expand through the interstellar medium. X-ray telescopes will observe the high-energy physics at play as material accelerates to near-light speed. Optical telescopes will track the cooling and recombination of the gas. Infrared telescopes will watch as dust forms and molecules assemble. The remnant will teach us about the physics of shocks, about particle acceleration, about how energy is transferred from the supernova to the surrounding environment. We'll be able to measure the exact composition of the ejector, how much oxygen was produced, how much silicon, how much iron. We'll see the layered structure of the explosion, with different elements concentrated at different radii. We'll watch as the expanding shell collides with the circumstellar material that Betelgeuse shed during its red supergiant phase. This collision will create beautiful, intricate structures, knots, filaments, rings, all glowing from the energy of the impact. And at the center, invisible at optical wavelengths but detectable in X-rays or radio waves, will be the remnant, either a neutron star or a black hole. If it's a neutron star, it will be spinning rapidly, possibly hundreds of times per second, and it might be a pulsar, emitting beams of radiation that sweep across the sky like a lighthouse. If it's a black hole, it will be nearly invisible, detectable only through its gravitational influence on nearby gas or through the radiation emitted as material falls into it. Either way, it will be a fascinating object in its own right, a compact remnant of a star that was once nearly 1 billion miles across, and we'll study it for decades, for centuries. The Crab Nebula, remnant of SN 1054, is still teaching us new things nearly 1,000 years after the explosion. We're still discovering details about its structure, its pulsar, its dynamics. Betelgeuse's remnant will be similar, but closer, brighter, and observed with far more advanced instruments than were available for historical supernova. It will be a cosmic laboratory, allowing us to test our theories about extreme physics, high-energy astrophysics, and the life cycle of matter in the universe. And perhaps most importantly, it will remind us of the connection between stellar death and planetary life, because the gas expanding from Betelgeuse will eventually mix with the interstellar medium, enriching it with heavy elements. Some of that gas will be incorporated into new clouds, which will collapse to form new stars. Around some of those stars, planets will form, and on some of those planets, perhaps, life will arise. Life made from atoms that were once part of Betelgeuse. In that way, Betelgeuse will live on, transformed, scattered, but not truly gone. Let's return one final time to the idea that we are made of stardust, because this isn't just poetic language. It's a profound scientific truth that connects us to Betelgeuse and every other star in the cosmos. Every atom in your body has a history. The hydrogen atoms, roughly 60% of the atoms in your body, were created in the first 3 minutes after the Big Bang, about 13.8 billion years ago. They've been around since the very beginning of the universe, cycling through stars, nebulae, planets, and now you. The carbon atoms that form the backbone of every organic molecule in your body, your DNA, your proteins, your cellular structures, were created inside stars through nuclear fusion. Carbon is formed when 3 helium nuclei collide and merge, a process that requires temperatures of hundreds of millions of degrees. This happens in the cores of red giant stars, stars that are smaller than Betelgeuse but follow a similar evolutionary path. The oxygen you breathe, the oxygen in the water you drink, the oxygen bonded to carbon in your tissues. All of it was created in the cores of massive stars like Betelgeuse, where helium fuses to form carbon and carbon fuses to form oxygen. The calcium in your bones, the iron in your blood, the phosphorus in your DNA, all created in massive stars in the final stages of their lives as they desperately burn through heavier and heavier elements, trying to stave off collapse. And the gold in your jewelry, the silver in your coins, the rare earth elements in your electronics. These were created in supernovae and neutron star collisions, in conditions so extreme they can barely be replicated even in thought experiments. You are not separate from the universe. You are not an observer standing outside, looking in. You are part of the universe. You are the universe, arranged in a particular pattern, conscious and aware for a brief time. The atoms in your body are ancient. They are travelers. They have been through cycles of star formation and death. They have drifted through space, collected in nebulae, condensed into planets. And now, they're you. When you look at Betelgeuse, you're looking at a process that created you. The fusion happening in its core, the elements being forged and ejected into space. This is how your atoms came to be. Betelgeuse didn't create you specifically, of course. The atoms in your body came from many different stars, scattered across billions of years of cosmic history. But stars like Betelgeuse did create you. And when Betelgeuse explodes, it will create atoms that will, billions of years from now, become part of new worlds, new life, new consciousnesses. The cycle continues, always. And there's something deeply moving about that realization. We are not permanent, we are not eternal, but we are connected to each other, to the earth, to the stars, to the entire cosmos. We are all stardust, all of us, every person, every living thing. And that shared origin, that common heritage, is worth remembering. Despite everything we've learned about Betelgeuse, despite all our observations and measurements and models, there are still profound mysteries surrounding this star. Questions that we don't yet have answers to. Puzzles that challenge our understanding. Let's explore some of these unsolved mysteries because they remind us that science is not about having all the answers. It's about asking better and better questions. We know Betelgeuse has enormous convection cells on its surface. We've imaged them, we've measured them, but we don't fully understand them. How many cells are there? Do they come and go, or are they stable structures? How deep do they extend into the star? How fast do they move? Different observations give different answers. Some images show just a few giant cells covering the entire visible disk. Others show more complex patterns with smaller structures. The truth is, Betelgeuse's convection is far more turbulent and chaotic than our Sun's. The cells are larger, the velocities are higher, and the physics is more complex. And we're still working to model this accurately. Our best supercomputer simulations can capture some aspects of the convection, but they struggle with the full complexity of the problem. Betelgeuse pulsates. Its radius changes. Its brightness varies. We've known this for more than a century, but the pulsations aren't regular. They're quasi-periodic at best, with multiple overlapping cycles on different timescales. There's a roughly 400-day period, and a roughly 2,000-day period, and possibly others. What drives these pulsations? Are they purely acoustic waves traveling through the star? Are they related to the convection? Are they caused by some deeper instability in the star's structure? We have theories, but we don't have certainty. And then there's the question of whether the pulsations are connected to the mass loss. When the star swells, does it eject more material? Is there a feedback loop between pulsation and wind? Again, we think so, but we're not sure. We mentioned earlier that Betelgeuse rotates slowly. But how slowly exactly? And why? Measuring the rotation rate of a red supergiant is extremely difficult because the surface motions from convection and pulsation overwhelm the signal from rotation. Current estimates suggest Betelgeuse completes one rotation every 20 to 30 years. But these estimates have large uncertainties. The true rotation period could be significantly different. And if Betelgeuse is rotating, is the rotation uniform? Or does the star rotate faster at the equator than at the poles, like the Sun does? We don't know. And if the rotation is non-uniform, does that create instabilities? Does it affect the convection? Does it influence how the star sheds mass? These are open questions. When we image Betelgeuse's surface, we see that it's not symmetric. There are bright regions and dark regions. The shape isn't quite spherical. Why? Is this due to rotation? Unlikely, given how slowly the star rotates. Is it due to large-scale convection patterns? Possibly. Is it due to localized ejection events? Perhaps. Or is there something else going on? Something we haven't considered yet. Some researchers have proposed that Betelgeuse might have magnetic fields that create asymmetries in the surface structure. Others suggest that the star's pulsations might create traveling waves that show up as bright and dark patches. We don't know for certain. You might think measuring the distance to Betelgeuse would be straightforward. It's one of the brightest stars in the sky. We have sophisticated instruments. Surely we can measure its distance accurately. And yet, different methods give different results. Parallax measurements, the gold standard for measuring stellar distances, suggest Betelgeuse is about 550 light-years away, give or take 100 light-years. But other methods based on the star's properties and theoretical models suggest it might be farther, perhaps 700 light-years or more. A difference of 150 light-years might not sound like much, but it translates into significant uncertainty about the star's true size, luminosity, and mass. If Betelgeuse is closer, it's smaller and less massive than we think. If it's farther, it's larger and more massive. And this uncertainty affects our predictions about its future. A more massive Betelgeuse might explode sooner. A less massive one might linger for thousands more years. We need better distance measurements. And they're coming. Future space missions like Gaia are refining our measurements of stellar parallax, and we should have more accurate distances to Betelgeuse within the next few years. We've discussed the possibility that Betelgeuse might have a companion star, but after decades of searching, we still don't have a definitive answer. If there is a companion, why haven't we detected it? Is it too faint? Too close to Betelgeuse to resolve? Orbiting on an edge-on orbit that makes it hard to detect? Or is Betelgeuse truly alone? And if it is alone, why? Most massive stars have companions. What made Betelgeuse different? Perhaps its companion was ejected in a gravitational interaction with other stars. Perhaps it was already a binary, and the companion already died, becoming a white dwarf or neutron star too faint to see. Or perhaps Betelgeuse formed in unusual circumstances that left it isolated. We may never know unless future observations reveal a hidden companion. And finally, the biggest mystery of all: when will Betelgeuse explode? We know it's in the final stages of its life. We know the core is filling with iron. We know the supernova is coming. But when? Tomorrow? 1,000 years from now? 100,000 years? The uncertainty stems from our incomplete understanding of the final stages of massive star evolution. How long does it take for the iron core to grow large enough to collapse? How does mass loss affect the timeline? How do pulsations and convection influence the end? We have models, but they're imprecise. They give us a range of possibilities, not a specific prediction. Some scientists think Betelgeuse could explode any time in the next 100,000 years. Others think it might last for 1,000,000 years or more. The truth is, we don't know, and we won't know until it happens. But that uncertainty is part of what makes Betelgeuse fascinating. It's a star on the edge, unstable and unpredictable, capable of surprising us at any moment. And when it does explode, we'll learn more in a few weeks than we've learned in decades of observation. Because nothing teaches us about the universe quite like witnessing a cosmic event in real time. In all our discussion of physics, stellar evolution, and cosmic cycles, it's worth stepping back and asking a more fundamental question. Why should any of this matter to you personally? You're not an astronomer. You're not a physicist. You're a person living a human life, with human concerns, human joys, human struggles. Why should you care about a star 650 light-years away? There are many answers to this question, and they're all valid. For some people, the answer is simple curiosity. The universe is vast and strange and beautiful, and understanding it, even a little bit, is inherently rewarding. It scratches an itch that humans have always had, the desire to know, to explore, to discover. For others, the answer is perspective. In our daily lives, we're bombarded with concerns that feel overwhelming. Work stress, relationship problems, financial worries, political anxiety, health concerns. These are all real and valid, but they can also feel crushing, all-consuming, inescapable. Looking up at the stars offers a kind of relief from this. It reminds us that there are things happening on scales far beyond our immediate concerns, that the universe is vast and ancient and full of wonder, that our problems, however significant they feel, are temporary and small in the cosmic scheme. This isn't about diminishing our concerns, it's about contextualizing them, putting them in perspective. When you're feeling overwhelmed, there's something deeply soothing about stepping outside, looking up at Betelgeuse, and remembering that this star has been shining for 10 million years. That it was there before you were born. That it will still be there after you're gone. That your anxiety, your stress, your worry, all of it is real, but it's also temporary. The universe continues, the stars shine, and you are part of it all. For still others, the answer is connection. Understanding that we're made of stardust isn't just a scientific fact. It's a profound statement about our place in the cosmos. We are not separate from nature. We are nature. We are the universe experiencing itself, thinking about itself, trying to understand itself. And that connection to the stars, to the cosmos, to the deep history of matter and energy can be deeply meaningful. It can make you feel less alone, less isolated, part of something larger and more enduring than your individual life. And then there's the simple beauty of it all. The night sky is beautiful. The stars are beautiful. The story of stellar evolution, of supernovae, of the cycling of matter through the cosmos. It's beautiful. And beauty matters. It enriches our lives. It gives us joy. It reminds us that the world is full of wonders if we take the time to notice them. Betelgeuse is one of those wonders, a red supergiant star visible to the naked eye, approaching the end of its life, waiting to explode in a blast of light that will be visible across the galaxy. It's there, right now, shining, and you can see it. You don't need a telescope, you don't need special equipment. You just need a clear night, a bit of patience and the willingness to look up. And when you see it, that small reddish point of light above Orion's shoulder, you'll be seeing something extraordinary. Not just a star, but a story, a history, a future. You'll be seeing a process that has been unfolding for 10 million years. You'll be seeing fusion, convection, pulsation, mass loss, all the complex physics of a dying star. You'll be seeing something that will one day explode, transforming itself in the most spectacular way possible. And you'll be connecting, however briefly, to the deep cosmos, to the story of matter and energy that began with the Big Bang and will continue until the last star fades. That's why Betelgeuse matters. Not because it's useful in any practical sense, not because it affects your daily life, but because it's there, because it's beautiful, because it reminds us that we live in a universe full of mystery and wonder. And because for a brief moment, when you look up and see it, you become part of something larger than yourself. There's one more idea worth exploring before we close. The concept of cosmic time and what it means for our own lives. We live in a strange moment in the universe's history. The universe is 13.8 billion years old. It will continue for trillions upon trillions of years until the last stars fade and the cosmos grows cold and dark. We exist in what might be called the golden age of the universe, a time when stars are still being born, when galaxies are still colliding and merging, when supernovae still light up the sky. In the far future, billions of years from now, star formation will slow and eventually stop. The universe will become dimmer, emptier, colder. Galaxies will drift apart as the expansion of space accelerates. Eventually, each galaxy will be alone, isolated, unable to see any others due to the vast distances and the recession of space. The stars that exist will age and die. One by one, they'll run out of fuel and fade. Red dwarfs, the smallest, longest-lived stars, will shine for trillions of years, but even they will eventually go dark. And in the unimaginably distant future, the universe will consist of nothing but black holes, dead stars, and fading radiation, all drifting through an ever-expanding void. This might sound depressing. The heat death of the universe, the eventual end of everything. But it's also a reminder of how precious the present moment is. We're alive during an era when the universe is still active, still vibrant, still full of light and energy and complexity. We can see stars, we can see galaxies, we can witness supernova, neutron star mergers, the formation of planets. Future civilizations, if any exist in the far future, won't have these opportunities. They'll live in a much quieter, much lonelier universe. But we're here now, in the Golden Age, the time when the cosmos is most alive. And Betelgeuse is part of that. A star living out its final chapter during an era when conscious beings can observe it, study it, appreciate it. One day, billions of years from now, there will be no more stars like Betelgeuse, no more red supergiants, no more supernovae. But today, there is, and we're here to see it. That's a gift, a cosmic gift, granted by the simple accident of our existence during this particular epoch in the universe's history. And it's worth appreciating. As we approach the end of this journey through Betelgeuse's story, I want to leave you with an invitation to wonder, to curiosity, to the simple act of looking up and asking questions. You don't need to be a scientist to appreciate the cosmos. You don't need a PhD in astrophysics to feel awe when contemplating the vastness of space and time. You just need to be willing to wonder, to ask, what is that? How does it work? Why is it that way? And to be comfortable with answers that are partial, incomplete, uncertain. Because that's how science works. Not by providing final, definitive answers to every question, but by gradually building up a body of knowledge, refining our understanding, always leaving room for new discoveries and new mysteries. Betelgeuse is a perfect example of this. We know so much about it now, far more than astronomers knew even a few decades ago. We've measured its size, tracked its pulsations, imaged its surface, studied its spectrum, modeled its interior. And yet, mysteries remain. Questions we can't answer yet. Puzzles that challenge our understanding. And that's okay. That's how it should be. Because the moment we think we understand everything, we stop looking. We stop questioning. We stop wondering. And wonder is what makes us human. It's what drove our ancestors to look up at the stars and create myths, legends, stories that connected earth and sky. It's what drove early astronomers to chart the movements of celestial objects, seeking patterns and meaning. It's what drives modern scientists to build ever larger telescopes, more sensitive instruments, more powerful computer models, all in the pursuit of understanding. And it can drive you, too. You don't need to dedicate your life to astronomy. You don't need to change careers or go back to school. You just need to look up sometimes. To take a moment on a clear night, to step outside and see the stars. To find Orion, find Betelgeuse, and think about what you're seeing. To remember that the light reaching your eyes left that star 650 years ago. To realize that you're looking at a dying star, a red supergiant approaching the end of its life. To know that one day it will explode and the sky will change forever. And to feel for just a moment connected to something vast and ancient and profound. That's enough. That simple act of looking and wondering is enough. It doesn't solve your problems. It doesn't change your circumstances, but it does something else. It reminds you that you're part of a much larger story. A cosmic story. A story that began nearly 14 billion years ago and will continue for trillions more. A story of matter and energy, of stars and galaxies, of life and consciousness. And for a brief, precious moment, you get to participate in that story. You get to exist, to be aware, to wonder. That's the real gift. Not just that Betelgeuse exists, but that you exist to see it. Not just that the universe is vast and old and full of wonders, but that you're here to appreciate them. That's extraordinary, and it's worth taking a moment to acknowledge it. Thank you for watching Infinite Science. The next time you see Orion in the winter sky, look for the red star on his shoulder. And remember, it's still there, shining, breathing, waiting. One day it will explode, One day it will transform. One day its light will fade and the constellation we've known for millennia will change forever. But not today. Today, it still shines. Today you can still look up and see it. Today you can still feel that quiet sense of connection to something vast and ancient and powerful. So take a moment when you can. Step outside on a clear night. Find Orion. Find Betelgeuse. The universe is vast. The universe is old. The universe is indifferent.